Okay, so let's start. So a couple of questions. First, did you guys, I mean, you see my announcements, right, from both undergraduate and graduate. I mean, because the class is cross-listed on Canvas. I'm just curious if my announcements through Canvas reach both groups of people, right? So what is happening is that we will have a quiz by the end of the week, right? So it will be assigned, let's say, on Friday, and it will be due by Monday, just because Monday night. And it will be a quiz, as I was saying, it's a timed quiz. You start it on Gradescope, you will have some limited amount of time to finish it since after you started, but you can start at any time, right? The goal is to just force you to go through the week of material. And what specifically you have to do is you have to do the assigned reading. So essentially it's online. Let me just start Firefox here. And actually after every lecture, I mean, it's already updated, let's put it this way, but if you, will be like minorly changed because the schedule is slightly changing. I cannot predict how fast we're going, right? So, but please take a look at the website schedule and just take a look and make sure that you read the chapters assigned at least by the time you do the quiz, right? So right now, if we did this lecture number 1, I assigned this chapter 2, which is introduction from this book, OS step. So operating system in 3 easy pieces. You can just click this link, go through the chapter and just read it, right? And it will be a very kind of like warm-up-y kind of style quiz, but again, I recommend you to do the readings, right? And there is usually a couple of optional readings, and this one is, again, remember I told you that the class will require you to program in C. It's a little tricky if you, first of all, if you've never done it. So how many people never programmed in C? Excellent. So we're safe, right? Then again, my recommendation here, chapter 5, which is pointers and arrays. There's nothing super complicated about it, but I just argue that you go ahead and revisit this chapter so you know how to, you know, what is a pointer, how to dereference a pointer, stuff like that, right? And so that's essentially what's going on. So we have a website, we have a Canvas Piazza. Again, I argue you should sign up on Piazza, ask questions. And Gradescope is coming on Friday with the first quiz for you. Question? Okay, good. Okay, so let's get back to the introduction. So essentially, it's still kind of a warm-up. My goal is to give you a high-level overview of what operating system is doing, right? So, and then it will take us the whole quarter to do it piece by piece. But I just wanted to make sure that you at least have some kind of a high-level understanding of what's going on. And maybe you do. I don't know, like where you are, right? So it's hard to judge before the first homeworks, before stuff like that. But it's okay. So even if you know all of it, so just don't don't fall asleep. So just again, my favorite drawing, right? So if you have a CPU, it has a pointer, a special register. What is the name of this register? Who remembers? Which points to the instruction which it will currently be executing? Instruction pointer, and the alternative names are program counter, or on x86 it's called RIP, just because this R stands for 64-bit version of this register, right? So CPU is connected to memory. This is your memory, right? And I'm reasonably good with straight lines, right? Remember that these are 2 different chips. So this is a thing which you buy in a like online, or it comes with your machine often, but it has a bunch of pins which are plugged on your motherboard. Okay, maybe that's a wrong idea to try to draw those pins. And the memory is a whole different chip which you buy. They're built with similar principles. Memory is much simpler, right? So it's just essentially has enough logic to retain the values in tiny cells, in tiny capacitors, either zeros or ones, and essentially either high or low voltage. And modern DRAM is built in such a manner that you have to refresh it every so often, because these capacitors are essentially losing charge, and eventually high charge will dissipate and turn into low charge, and one will flip to zero, right? And so DRAM, essentially, the logic of this chip, so there are some gates here, right? Like, I don't know, I'm drawing gates here, I don't know. Which essentially read a roll periodically, essentially just do a read operation from those capacitors and do a write back, right? It takes a little bit of time. So there is a certain overhead for this DRAM, but still this is the design which we use today. So does anyone know why we use this design? So because there are ways to build memory which doesn't have to be refreshed. So for example, memory which is sitting here on the CPU, and what kind of memory we know which is here on the CPU? So again, registers, one. So what else? Cache, that's right. Registers. Registers are essentially just tiny memory locations. They are not far. Imagine you have a cell here. Oh, I mean, it's not a cell, but like a region of this memory which allows you to hold 64 bits, for example, right? Registers is a single register is a very similar thing. So it's a memory which holds 64 bits. It's just used by the CPU in a special manner, right? And this memory is built slightly differently, so you don't have to refresh it. So there is a way to connect the gates in such a manner that they store information, right? It's called a flip-flop. I don't know if you took the engineering people are way ahead of me, so my knowledge is very basic, but at the level of computer science, there is a way to connect those gates in such a manner that it will remember the input on the rising edge of the clock or falling edge of the clock, right? And it's okay, so meaning that if you provide one when the clock is rising, and what is a clock? It's just an input to those gates, right? It's a signal which goes in a shape like this, right? And if this, at this point, if you provide one to this flip-flop, it will remember one. If you provide zero, it will remember zero, and we'll keep remembering it, right? Until the next rising edge of the clock, right? But the reason we use DRAM is that if we want to build a flip-flop, which you don't have to refresh, you need certain amount of gates, transistors. So let's say 4 or 6. I don't remember exactly the number. But in this DRAM design, which you have to refresh, or you can get away with just a single capacitor. So it allows you much higher density and much lower cost, right? So essentially, this is a trade-off. So you pay a little bit of a price. It gets a little bit slower, but it's much more denser. So that's why you use this. The idea that a single capacitor can store a bit of information, but you will have to refresh it, right? But okay, so it's a little bit of a detour. Just caches are also built out of gates just because we want ultimate speed out of them. And there is a little bit of memory on the CPU as well, right? But caches are transparent, right? So you don't really know about them unless you care about performance. But if this is memory, right, and you have this instruction pointer which points into memory, there will be an instruction sitting here, right? And CPU will read it from memory through a memory bus. We'll put it in like temporary storage, which is not even a register, just like some collection of gates, and we'll just do some operation, like for example, addition, right? And the CPU will go on and will start executing instruction by instruction by instruction here. If you have a jump instruction, right, maybe the value of instruction pointer will change. You will start executing instructions over here, right? So relatively simple, agree? The question is how to get from this very minimalistic idea that CPU just executes an instruction by instruction to something what we see on the screen, like a collection of windows with all these gadgets all over the place. This is, I'm drawing my screen, right? So how? So like what's between? And this is essentially the topic of this class. So how do we get there? How do we get to this three-dimensional view? And at a high level, it's relatively simple, right? So let me give you an overview of what, like, again, what is it class called? Principles of computer organization, right? So essentially, if you take a program in C, right, or any other high-level language, the compiler essentially, like a C compiler, will turn it into a collection of instructions, which we can call an object file, right? So those instructions which are here will be stored here in this file, right? The operating system will be manufactured in a very similar manner. So out of a collection of different C files or maybe assembly files, you again get a file which contains machine instructions, right? There is a protocol which is called a boot protocol, which allows you to essentially place a tiny bit of these instructions in a specific address, which is coordinated between the software developers and hardware developers. And operating system will start, actually this typically is on disk, and the hardware will essentially read something from this disk from sector 0, load it in memory at a well-agreed address, OX7 C00, I believe, and will configure the CPU instruction pointer to start executing instructions from this address, right? And then it's up to you. So essentially, if you wrote some code here, which is beginning of your operating system, you can do anything. You say, look, I start running here, and then I maybe will go read something from a disk. So this file, which is stored on disk, you will load it in memory here, and then configure instruction pointer to start executing instructions from here. So imagine this is the beginning of your main program, right? Main functions, sorry. So far so good, right? So it doesn't look very complicated. So we just have to figure out how to, like, essentially what to write in this original components here. We'll do that in a couple of weeks. So it will be a lecture about system boot, right? Then we will take a look at how we compile programs like this. Imagine this is a hello world program. So this was hello.c. We compiled it into executable file, which is hello. Let's say, what extensions do you want? There is no good extension on Linux. Let's say A. For A is a container, just a file format which allows you to store instructions. Typically it's ELF, but ELF doesn't have a good extension, right? And then figure out how to essentially read something from disk, load it in this memory, and start running, right? So any questions about it for now, for a second? Good, you understand what's going on? Okay, so now the question is, again, imagine we want this three-dimensional view, right? Like, essentially, let's start with something simpler, even. Imagine we just want to see on a screen letter H, beginning for hello. Because what we want to do is we want to start with this file and essentially make sure that we can print hello world on the screen, on a real screen of real hardware. So how do we, who knows, how do we output this letter H on the screen? I was mentioning this in passing, and don't worry, we'll cover a lot of it, but maybe someone knows. Anyone?
But H at a special location in memory.
Correct. So your classmate is saying, so what you have to do is put a set value, which represents H, at a specific memory location, right? But it's not on the screen. So what happens next? How does it get on the screen? Do you guys know?
You have to use like system service hours or something like that.
Well, not sure that I understood what you said, but imagine everything is as simple as I was talking, as I was describing. There is no system call, nothing. It's just hardware, your compiler, and your language, maybe bits of assembly. So what happens to this H?
So where do you want it to be?
Correct. So this is like very mechanically, you write H into this memory location. Let's say OXA, guessing here, some number of zeros. Haven't done it in years, but how does it get on the screen? Yeah.
Just to guess, the OS checks that memory location occasionally, and then it has like some instructions that do that.
Reasonable, but there is no OS yet. You're writing this OS.
My guess that this buffer in memory is a location that the screen will automatically check, and every time it refreshes, it just pulls in the location memory
So what checks this?
of the screen.
The screen, exactly. So great. So, okay, this is a detour to explain you how device drivers or how devices work, right? So remember I said, let me switch to the slide deck and I will scroll back a little bit. I built this diagram of the machine here. Let me just, this one. Wait, was a little bit of a delay. Yeah. So what happens here is, oops. And where is it? Delay confuses me. Yeah. So this is an architectural diagram of a typical machine which you're using today. So this is my laptop. This is my phone effectively. This is a server, or the server might have more of these CPUs here connected like this, just because we typically run multi-CPU servers, right? But what's important here is this, there is this connection of buses, right? So CPU itself connected not only to memory, but to a bus which connects peripheral devices. And let me just briefly explain what happens here, right? So, and your screen, your VGA, or like, let's say your GPU will be also connected here, right? GPU here to this bus, right? Let me explain what happens when you write this H. So again, so the hardware vendors agreed with software vendors which build operating systems that the hardware, and let me just erase a little bit here. We don't need this probably. We don't need this either. So when you run into this memory location, which is just 1 byte, right? Because H can be represented ASCII, another acronym. Let's say it's 1 byte for now, just bear with me, although there are different ways to do this. So this piece of GPU, which you connected on this bus, right? It also has a CPU inside, right? And I mean, not a big surprise, NVIDIA is like a super duper CPU. It's not just the CPU, right? But let's imagine we have some simple VGA card. So the CPU can actually run an operating system. It's typically called the firmware, but essentially the toolchain which you use to build the software or the firmware which runs here is very much as we will use for building the operating system. C, assembly, C is probably even better. And there will be a CPU. Maybe it's an ARM core, maybe it's some wimpy MIPS core, but it will be there. And maybe some of it is a silicon which is designed to do frequently executed operations, like essentially reading those locations in silicon, right? So what happens is that when you do this write into memory, remember I said that CPU is connected to both memory bus and this device bus, which I was calling PCI. And I think it's called stands for something like peripheral. What is that actually? I forgot. Okay, I will look it up for you, but don't worry. But the deal is that this region of memory is registered with the CPU in such a manner that the write doesn't go to memory. And instead it shows up on a PCI as a packet. Essentially, kind of PCI acts as a network and sends, okay, look, there's a message and it's coming to you. Not all this memory sends packets, but okay, there are multiple ways to do it, but essentially both the device through this PCI bus can read this memory and both CPU can write something into this memory. So it kind of becomes like a communication interface between the device and the hardware, right? And so as your classmate said, this logic of this device partially implemented on a CPU and some of it is like implemented as in silicon just to optimize it, periodically pulls the whole memory location. This is called a frame buffer. And essentially says, okay, this is H here. I know that this corresponds to the position, like those are pixel. I mean, if you zoom in, what you have to draw something like those are pixels, something like that, right on the screen. So what is a screen? It's just a collection of, if it's an LED, it's a matrix, right? So, and this thing essentially through the cable can send commands and say, okay, please change the color or light them up and stuff like that, right? And so essentially, you write a byte here, which represents H. I forgot what this byte is, let's say F something, right? The hardware of the GPU pulls this memory with like, let's say, with a frame rate, 60 times a second, for example, right? And does a little bit of a conversion saying that letter H should be represented like this on the screen and essentially lights up the region of the screen with, like, control the LEDs and says, okay, like this will put this shape on the screen. Yeah.
At what point does the H get converted into actual pixel value? Is that on the CPU or
On the GPU? At least in this story, I believe, yeah. So because what you write here is just a byte. Let's imagine a very simple thing. So there are many things which can happen if it's a, you know, like a game engine and there is like a lot of rendering and I'm like, I don't really know this domain. And at some point you might do a bunch of computations and the frame buffer itself might be even hosted here, if I understand correctly, but let's not go into those details. So just imagine this is a letter H. So the hardware has a little bit of knowledge how to convert H. Essentially, this is not the H which you see on my screen here. This is more complicated. So those pixels will be generated in software, like here by the rendering engine of your graphical user interface. But when you just barely boot, you see those letters. Let's just talk about those for a second. There was another question.
I didn't completely understand what does the PCI network are. You said it acts as a communication.
It's this bus. And think of it as a network which can send packets. And there is logic on the CPU. Like I told you, there's like instruction pointer, which executes programs and stuff. There is some other logic which runs in parallel, which can talk to this bus and allows the device, for example, say, okay, please read a region of memory from here. And your IP is not even involved in it. So everything is done with a different logic on the CPU. It's called direct memory access, DMA. And so your operating system doesn't even notice, but the memory gets read by the device or written by the device. Does this explain? And this, just to make, there are like hubs potentially, which it becomes really a network without, like, it's largely hidden from you. Any other questions?
How do they multicast these messages on the bus?
Oh man, that's a good question. So let's not go into this. So like implementation of a PCI is outside of school. Just think of it as a network. Like in the end, some hardware logic on the CPU knows how to send those messages, ensure reliable delivery and stuff like that. Knows where to send this message and stuff. But I don't want to, first of all, I don't know the details. And second, I don't want to go into the details either because we'll spend like hours.
So what the CPU does is send a text or message to the driver asking to print the edge on the screen. Is that correct?
Correct. So although it's not a driver, this is a device. Wait, sorry. Right, so it's your real physical card which you plugged on the motherboard in a PCI slot, or sometimes it's soldered, or sometimes it's even on board of a PCU or of a CPU. But okay, so if we know how to print this letter H, right? That's kind of already good, but and that's fine. But we still want to run multiple programs, right? So we want to run multiple screens. And this is where it gets a little bit, again, interesting. And this is what I was trying to explain. And we'll finish explaining today. But imagine you have multiple programs. So one of them was, let's say, blue. And let's say you compiled another program, which is green. Originally, they both sit here on disk, right? Blue and green. Operating system knows how to read them from disk and load them into memory. So we said that this blue one was loaded here, right? And operating system will load green one into a different location in memory, right? And the magic is that it will, I mean, itself operating system, let's make it yellow because I usually draw it yellow. Although I don't know if yellow is well visible on this screen. Let's make it orange for the sake of it. Sits here in memory somewhere, right? And what it does is that essentially it knows how to switch between them, right? And it's called a context switch. So essentially, at some point, either this, remember I was saying, either this blue program says, I have nothing to do and I will invoke a yield, or as I will explain today briefly, a timer interrupt is delivered and essentially preempts execution and passes control back to the operating system. Operating system decides, it kind of makes a scheduling decision, whose turn is to run next. And it says, okay, maybe it's blue was just running, so it's green's turn to run next. And it will configure instruction pointer to point to green, and then green starts executing and essentially do something, right? Let's say if you just compute numbers, it's kind of like clear, right? And it goes back and forth, right? So everything sits in one memory, and like it's instruction by instruction by instruction, right? Green might also write something. Maybe green will write world here, right? And it's not very nice because green and blue can overwrite each other on the screen. And so in a typical system, what happens is that those programs, green and blue, they don't have permission to write into this region of a frame buffer. And instead you will use a third program. Let's draw it as red, which, I don't know, I'll call it a compositor. But it's a part of your graphical user interface, which essentially will communicate with green and blue. So green will kind of write its own text, hello, and blue will write its own text, world, into two buffers, which will be, let's just say, located here in memory and somewhere over here in memory, but they are not, the hardware doesn't touch this buffer. But what the compositor is doing, compositor will essentially say, okay, I have access to those buffers. Wait, where is it? So these two. I know that maybe blue is running underneath green, like it has the notion of a z-axis, right? And essentially says, I know that green is on top, blue is behind, sorry. And it will essentially assemble this view. So maybe, so this is a world, and this is hello, right? And it will assemble this view in this region, which is known to hardware, right? So this compositor will have access to this hardware buffer, like essentially drawing here one window on top of another, and then the hardware essentially just again reads it and puts it on as a collection of pixels, right? So any questions about this? Is it clear? So reasonably simple, right? So at least right now, you can understand that, okay, if you just give me a little bit of knowledge and I will program this component, which boots the operating system, reads files from disk, loads them in memory. If you say, okay, I want to build a graphical user interface, you can also program this compositor. And after that, you get essentially what you have on your screen, right? So, and our goal in this class to essentially learn how to do it over the course of a semester. So we will start soon by essentially understanding what parts have to go into this component, which implements operating system, how to boot machine, essentially get to the point when you can start running main function of your operating system kernel, right? This here, for example. and then how to essentially load programs in memory and execute them, right? And just a little bit of a terminology, right? So typically, this thing, which is a operating system itself, is called, or this part of the operating system is called the kernel. And those guys, like my green and blue programs, they are called processes, right? So process has a kind of associated memory location, which stores instruction and heap of the program and stack, and has a context of execution. So essentially like the value, current value of instruction pointer and general registers, which the program is using. And if the operating system switches from one process to another, it will save those values from hardware registers into some temporary locations in the operating system memory over here, right? And just load them later when this, again, time, it will be a time to run this program again, right? So this is a process, right? And if you suddenly have multiple contexts of execution, which run within the same memory, those contexts are called threads. Right? So threads, multiple threads can run inside a single process. It's useful for specific purposes. Sometimes the process one context of execution gets blocked in a kernel waiting maybe for input output, like reading a disk, but maybe another thread has to do something to like put this progress bar or something right on the screen. Is that clear, this terminology? And again, we'll come back to it. And one of the homework assignments will be to extend x86 with threads, because x86 only has processes right now. All good? Okay, so this is my wonderful drawing. I'll save it, put it online. Let me just, where do we want it? Sure. And let me get back to the slide deck to just like finish the intro. So but this is essentially, I will be drawing the same stuff like this. So it's again, like yellow kernel, which implements operating system functionality, blue and yellow program, or blue and green program, right? With main functions, right? But we kind of know where it is, like it's in memory, CPU just, fetches instructions, operating system just switches instruction pointer between blue and green periodically. And for you, because you're a human, it happens so fast you don't even see, right? Although if you ask me a question, how many things are running on my operating system, I can actually quickly come up with an answer for you. So there's this PS, which shows all the processes in the system. And if I do count the lines, it comes up to 367. So 367 threads of execution are running on my system right now. Why? I mean, we can explore what each of them is doing. Some of them are service threads, right? And like myself as a user, this is this bash, but it doesn't matter. So anyway, so we got the point. So we have to context switch or switch between programs, right? So we first run one, then run another one. And it's very much kind of like a sharing the resource, because you have one CPU, right? So it's like you have one car or one bike. If you're a kid, right? And it's a new bike, everyone wants to run it. So you have to take turns, right? And it happens over and over again. I briefly touched on this, like when I say, when I switch from one process, from this green process to a blue process, what state do I have to save? What do you think? What is the state which we have to save? Yeah. Exactly. So we have to save the registers, right? We definitely know that we have to save this instruction pointer, right, which was pointing into green, and we now since we want it to point into blue, we have to save it. Where do you think we save it? Like, you will likely design a data structure, which you will call something like struct proc for process, right? And it will have a field like, well, unsigned int, let's say IP, right? And you will save it here, and this data structure will live in the memory of the kernel, like most likely on a heap, because you will be dynamically allocating those data structures for keeping track of like unknown upfront number of processes, right? And so this will be state of green, and there will be another data structure. Maybe you will keep them as a list or maybe as an array, and this one will be representing blue. So essentially, the operating system itself here, it's very much normal C code, which will just write this value, read the register with an assembly instruction, and put it in this data structure, right? This is a save. And then the context switch will be essentially save the values from green and load the values of blue and start running, right? With a little bit of like protection mechanisms, right? So this is true. So you have to save the registers. Memory is a little tricky. We'll talk a little in a second about it. And you have some data structures like the state of the process, which is maintained by the operating system itself, right? So open files, open sockets, stuff like that, right? And this state is already kind of saved, right? Because what I would say is that normally, if you want to have some open files, you might have some information about them, maybe as yet another array here, and it's already part of this process data structure. So you don't really have to save much. So you just have to switch from one process data structure to another, right? And we will get to this again. We will see the implementation of this process data structure in x86, right? So I said that memory is a little bit tricky. What do you think happens to memory when you switch from one process to another? Yeah, so you're well educated. So I wanted to do like this funky detour saying you have multiple processes, one memory, and I was drawing it as one memory, right? One physical memory. This is one real, like this is my DRAM banks, right? And this is continuous address space starting from 0 going to, let's say, 16 gigabyte, right? And the question is like, what happens? Do you really have to copy out the entire memory and put it on disk, for example, and copy back in? And you say, wow, it's in theory possible, but it feels so slow that this is not how it's done. And instead, what you just said, what happens is that you have a notion of a virtual address space. A virtual address space essentially allows you to say that one process, although it has a logical addresses from 0 to, let's say, 4 gigabytes, it's a real number, 4 gigabytes on a 32-bit architectures, right? Has access to a subset of this physical memory, right? And there is a notion of paging, meaning that we split this memory into regions of identical size, let's say 4 kilobytes, which is again a real number. And there will be some kind of a hardware mechanism which allows you to figure out a mapping of this address, which is called a virtual address, into a physical address here, right? And so the idea here is that the process and, like, for example, two processes here, green and yellow, despite the fact that they might have an identical address here, so maybe this one, let's say 1, 2, 3, let's say this X matches this X here, right? It's the same address, it's the same value. Let's say it's I don't know which address we wanna. It's like 4K multiplied by 2 plus some delta. So what is it? 8. Let's say 8,250, right? So this is the address, and the same address, 8,250 in yellow, in reality will be backed up by different physical addresses. So one is here and one is here, and there will not be overlapping, and it's called a virtualization of memory. And it's done with this notion of a page table, which we will cover, but effectively you don't have to do anything. So you essentially just switch the page table. So let me explain how it works. So the hardware itself will have a register which points to the current page table. On x86, this register is called control register 3, but you can call it as a register which points to the page table root, right? And when you switch from the green to yellow, you just change this register and it points to another page table, which maps now the memory of the yellow process, right? So this way, each of them, green and yellow, has an illusion that it has the full 4 GB address space, but in practice, it might have holes in the address space, which are not mapped at all by physical pages. And physical pages might be sitting anywhere in physical memory, in some kind of semi-random order, which is chosen by the operating system, but they will never access pages of each other unless you specifically configure those page tables to enable sharing between processes. And an example of sharing, which we've seen today, is the sharing of memory between the graphical application and a compositor, because compositor reads memory of each graphical application. So, and reading means that there will be a page somewhere over here and somewhere over here, and those two pages will be mapped into a single hardware page. So both of them can read the same page. We'll go through this in a lot of details later on, but just a heads up. Question.
What if two processes both need one happen for memory? They don't realize that at all.
Sorry, I missed the beginning.
What if each process uses more memory than it should in the protocol physical memory?
Right. So, and this is a idea which was like very, important in the past when I was a child, because my first machine, which I got as a gift, had only 16 megabytes of RAM. 16 megabytes is laughable. You know, the last level cache of a CPU these days is like 32 megabytes. I had 16, right? So some of those games which I wanted to play didn't fit in my physical memory because the number was 16 megabytes. And operating system back then was designed to, and still now, but now it's less important, was designed to essentially save those pages temporarily on disk. The idea which is called paging. So essentially when you say, look, I want another page here in this green process, imagine all of these pages are already taken. What you do instead, you say, okay, I have an algorithm and I detect that one of those pages wasn't used for a while. So I'll classify it as a cold page. And I will save it to disk and I will remember, I means operating system, that I saved it to disk. This page becomes free and you essentially map this page into this address, letting the green temporarily use this physical memory. And if later on this yellow says, okay, you made a wrong judgment, I actually need this page, I try to read memory from this. This mechanism of pages allow you to detect the fact that this page is not mapped, generate an exception, which is called a page fault, and we'll go through exceptions later in the class in details. We'll see x86 doesn't have paging support, but we'll understand how it works. It has page tables, but doesn't have page, this idea of saving pages to disk. And at this point, operating system says, okay, look, you really, it's your page, it's on disk over here. I need to allocate yet another page. So maybe it goes through those pages again, figures out that now this page is idle, because it wasn't accessed. It saves this to disk, loads this old page into this location in physical memory, and configures the mapping to make sure that this old address maps to this page, right? So it's like complete virtualization. So kind of again, if you think about cars, you say, I really need a car. Maybe you say, I want an SUV, and it's a time-sharing service. So you will get an SUV. It will be a different SUV, but it's an SUV, right? And in this specific case, it's an extra service here. If you left a pair of skis in your old car, it will magically show up in this new car as well, because they saved the skis for you, right? And you can go skiing. So this is paging, right? Any other questions? Good. Okay. So there's a couple of things here which are kind of important because originally, and this is how it was historically done. So people were first willing just to run stuff, timeshare, run, complete, get some numbers out. But really, there is in a modern world, because those programs are deployed by third-party people, right? You never meet them, right? You pay them money to deploy some functionality, right? You don't have to trust them, and this is the problem, right? So a concrete thing is that imagine a program which you launched, maybe it's a web browser, often actually fails to release the CPU. It just like spins because there is so much work that it just says, okay, I need to run a little bit more, a little bit more. Remember, I was saying that yield is the thing to call to pass control, so operating system can switch into another process here, right? But imagine this yield never happens. Maybe yield is here, and you're running in this infinite loop in this program. And so there's clearly a problem, right? So what do you think we're going to do? So how will we change the hardware to support this thing? To essentially make sure that no one can take the CPU forever, no process in the system. What would be an idea? Have a timer, right? Exactly. So remember, I keep drawing those buses, but at some point people introduced a piece of logic, which used to be a separate piece of silicon, but now it sits on the CPU itself. And you can configure it to send a signal to the CPU after a certain amount of cycles, which translates to time. Let's say 10 milliseconds. It's a huge amount of time because on a 2 gigahertz machine, how many instructions will be executed in 10 milliseconds? What?
20 million.
20 million, correct. At least, right? I prefer to say 20 million. I agree with that. So do you understand how we did this counting, right? So it's part of the, okay, I can explain it well, but it will take me forever. So let me just explain it quickly, which will take me less than forever. But so again, depending on how well you know how CPUs work, CPU is designed as a collection of stages which implement something what is called a pipeline. So remember my fetch, decode, execute loop, which I was talking about. So imagine the first stage, and what is its stage? It's a collection of logic gates. I mean, maybe a million of gates, right? But they implement certain logic. Depends. It's kind of like an algorithm which you code and then it gets translated to gates. Instruction fetch, then instruction decode, maybe instruction execute, maybe let's say access to memory, and so on, right? And typically, one of these stages is designed to take exactly one cycle. The CPUs run a specific signal which is called a clock, right? And who knows why we have this clock signal? Why do we need it? Does anyone know from the architecture?
To synchronize each component.
And when you say synchronize, what do you mean?
Make it neat.
Make it what?
Organize.
Organize. Any other?
To make sure so that whenever instruction fetch will be done by the end of that cycle, and so instruction decode and say, okay, I now know when instruction fetch is done, so you make sure everything is done within your clock.
Exactly. So when you say organize, clock is specifically used to save intermediate results. So between those stages, there will be, let's say, a latch. It's kind of like a register, a memory, which allows you to say, by the end of this time, let's say it's 2 gigahertz, 0.5 nanosecond, right? The result will be available and will be saved in this memory. And then when the next stage starts running, it will read from this memory. And although maybe this stage is already processing something else, and those gates is already like the signals are propagating through the gates, and maybe this memory, like the output of this stage starts changing from 0 to 1, 1 to 0. So it's kind of in volatile state, not yet converged. But the second stage reads the memory saved at the beginning of the cycle. Because remember, I mentioned that these memories can be designed that they remember the values at the rising edge of the clock, right? And so these memories essentially just keep the values until the end of the cycle. Maybe it's 15, right? And maybe this one is already computing something to this, like outputs will be first like 17, 27, and then it will converge to something like 32. And this 32 will replace 15 on the next writing clock of the cycle, right? And typically, and the pipelines are used to make sure that you can, because execution of the entire instruction might take you, let's say, 3 nanoseconds. That's a long time, meaning that you will get a new instruction executed each 3 nanoseconds. If you split it in those stages, right, now you roughly seeing a new instruction completed every 0.5 nanoseconds, right? Because it's kind of like an car assembly pipeline. You start at one car, you move it to the next stage, but this first stage is already processing the next car. And so this is exactly the same idea. You say like, it takes an hour to assemble a car, but since stages are like 10 minutes each, I will see a new car every 10 minutes, right? The same with instructions, right? And so this clock means that roughly you will see one instruction coming out every 0.5 nanoseconds, because this is the length of our clock, right? And this corresponds to 2 gigahertz. Like if you just do the math, it just means that it oscillates that many times per second, right? And if you do the if you multiply it by 10 milliseconds, which is 0.01 second, right? You will get 20, because if you multiply this 2 billion by 0.1, you will get 20 million. That's why it's nice to know how instructions correspond to physical time. And sometimes instruction gets stuck here because memory is slow and you have a bunch of idle cycles, nothing is happening. Sometimes you go a little bit faster because CPUs are designed to execute multiple additions within a single cycle. Sometimes you will see something like 0.5 instructions per cycle, but let's keep it simple and say 1 roughly, right?
Won't be the 2 gigahertz be based on the time of the clock for 3 nanoseconds rather than the time to the instruction before that one?
No, again, I missed the beginning, sorry.
Sorry, so wouldn't the 2 gigahertz be based on the 3 nanoseconds rather than 5 nanoseconds? I thought the first were based on the clock speed rather than the pipeline instruction.
No, okay, let me explain. So you can choose the length of the cycle. You can say instead of 0.5, let's do 1 nanosecond. Clearly it will run slower, right? Or let's choose it to be 0.2 nanosecond, right? So what happens if you choose it to be 0.2 nanosecond? It means that you say that each stage of your pipeline, and it's kind of like a tiny sea of gates, right? Which is complicated, and the signals are propagating across them, have to reach a stable state in 0.2 nanoseconds now. It might happen, might not. So what you do is that you do an analysis and you know that each of these gates has a clock delay, something in the order of picoseconds. And depending on how long your computation is, you say that defines my cycle. That's why essentially the hardware implementation and in the algorithm which you, for example, imagine something like division is clearly a long operation because you do it iteratively, right? So it takes multiple cycles. It's not even done in one cycle because it would be prohibitively slow, right? But essentially your goal is to, as a CPU designer, to come up with a clock cycle length which accommodates every stage. And sometimes you say, well, this doesn't fit, so let's split it in 2, essentially. And then your pipeline gets, it's kind of, again, the car assembly line. So we cannot finish painting. Okay, let's paint half of the car and paint the other half in the second. But still we will get, the processing of the car gets even a little bit longer because you have to save intermediate results, right? In this latch register, but really it's roughly the same, let's say 1 hour, but now you get a car every 10 minutes anyway, right? Is that what you asked?
Yeah, I was confused. My bad. I saw 3 nanoseconds. I hate 10,000 clock. 10,000 clock. I think it was actually in full instruction. How long takes it to complete instruction?
Right, roughly, right. But again, wait, I was answering this question last time after the class. So if you don't understand this at all, my recommendation, there is a great instructor here, Rajiv, and he teaches this class. which is a computer organization. I also teach this class, but I'm worse than Rajiv, and I admit it. So I do operating system. He does architecture. And Rajiv recorded a set of videos, and they're like 10-minute videos, starting from one. And he goes over like organization of a MIPS CPU, how to get through from gates to state machines, like saving the state, flip-flops, then goes into pipelining, caches. I mean, roughly, let's say 81 video multiplied by 10, 810 minutes of watching. It's doable over the long weekend, which is coming, right? I watched these videos myself many times. First time I watched it, I was like, this is great. I finally understood it because, I mean, for a while, like I also cycles, gates, who cares? I mean, I was building systems, right? But those are great videos. So I recommend him as it's almost Khan Academy style. So not hard, very watchable. And he doesn't like dance in front of you. It's all like professionally recorded and stuff like that. So, I mean, not professionally, but very well done. So recommend watching it. So I will put it on the website because I've seen a couple of those questions, but we don't understand what cycle is, right? So let's make sure that we understand. Okay, so we got this. So but as a systems researcher, hold on, like this is the final thing which we need to remember. You need to be able to quickly come up with those numbers. I mean, it's part of your life. Why? Because when I was young, you know, CPUs were getting faster, 2x faster every 4 years or something like that, right? Moore's law. They stopped, right? So CPUs are kind of as fast as they get. They've reached physical limits. There is a lot of like emphasis on optimizing the software. So sometimes, you know, being able to say, I have this for loop which does something, how many cycles it takes, what is it in physical time? Imagine you have a packet arriving on a network, which is a 10 gigabit or like 40 gigabit network. How much time do I have between packets? That's a good question. Do this computations for 10 gigabit network, right? So, and like you say, like how many cycles I have to, like the fastest DPDK framework, which is data plane development kit, which is a very fast device driver for processing network packets, can process small network packets, 64-byte network packets in like less than 100 cycles. Think about it, read it from the network, from the device driver, do something and send it out in 100 cycles. So it's roughly 200 instructions. It kind of, this is where we are. So you have to do a lot of those optimizations. I will go through these exercises. We do them in when I teach my version of this computer architecture class, which I just cited, Rajiv's class, right? So in mine, we do a lot of those eyeballing, and it's a useful skill to do that, like especially if you're looking for well-paying jobs or just curious, right? Okay, so a operating system obviously needs to do another thing. It has to provide some kind of fairness in who takes control over the CPU, what runs next, right? Essentially just, this is the question. Pick which application is running next. And if I use this analogy with a bike, imagine you have a bike, you have 5 friends and you said, okay, we will have a fair share of a bike. First of all, what is fair? What if you're sick for a day? Do you get the bike for like half a day next day? It depends on how you define fairness, right? Sometimes you say, no, you're sick, you're out. Next day we still will get like 20 minutes each, right? But sometimes you say, no, it's if you were delayed, like went to have lunch, when you come back, you have a chance to catch up. Same here with operating system and processes. So there are different scheduling policies which, depending on what you're trying to achieve, right, implement a different scheduling algorithm. And it's part of the operating system inside. I was saying that you don't trust applications anymore. So maybe this one is your web browser and you're trying to do some online payment to some bank, for example, and here you run some application from an unknown origin, right? I don't know, like, let's say a game. Maybe it's a piece of malware, which only goal is to read memory of this application and essentially read your password to make sure that you can transfer your big Bitcoins to somewhere, right? So that's why despite the fact that early operating systems didn't care about it, this ensuring the isolation, meaning that one application cannot read the memory of operating system and cannot read the memory of other applications, is very important. It gets kind of deep, like enforcing isolation gets hard, but at some shallow level, it's just isolating memory and state, right? So if you don't have any isolation, you kind of like analogy of an open office, right? But it's no longer used, and you put processes P1, P2, P3 into those cells, which are completely isolated, and they can only exit. How do they exit? Do you guys know? How do they communicate with the external world? Because if you isolate something, right, you need some communication mechanism, a way for them to communicate between each other. So how do we do this? I will skip this one. This is the idea of system calls, right? So remember, I told you that at some point you can view operating system as a library, which provides some fancy functionality. And our goal next week to figure out what this interface will be. But this interface is called system calls. So the application can, like in a controlled manner, invoke a function in a kernel. So it cannot invoke any function here, but there is kind of like an entry mechanism which validates the correctness of the invocation, correctness of the passed arguments, right? And it lands on a specific system call. Maybe it implements a file open, for example, right? And there are system calls which allow programs to communicate between each other. So I mentioned that you can share memory between compositor and others, and shared memory is a very fast communication primitive. Historically, Unix kernel provides something what is called a pipe. So it's a way to write some kind of like stream of data into a pipe, and then another on the other end of a pipe, you can read the same stream. So it's kind of like a stream in network, but on a single machine, right? So that's how you communicate. So the reason for this slide is really to emphasize this term, system calls, right? So it's an interface between the operating system and the process, right? It's very limited. In x86, it will fit on one slide. So roughly like 12, 15 system calls, but powerful enough that you can run almost anything what you can imagine. Obviously, operating system implements something what we know as files and network, right? So because normally, if we want some kind of mechanism to save data which we computed, right, save intermediate results, really what happens is your permanent storage, something like a disk, it's very similar to a memory. It's just an array of bytes. So you can say, instead of bytes, you write blocks of essentially 512 bytes, right? And you say, wow, it starts at block 0 and ends at block, I don't know how many blocks, but let's say, what is it? Like 2 terabytes, for example, right? But it's really like blocks. This is the disk. Of course, as a human, you say, well, can I write individual blocks? Well, it's very cumbersome. You run into issues, right? So maybe you have to keep track of which block represents what file and stuff like that, right? And this is what is done by the operating system, which implements something what is called a file system. So essentially provides you a human readable interface to a block device. So you have names. So for example, you say, I have a file which is called context.txt. You can open this file, and the operating system figures out which blocks on disk essentially back this file, right? And ensures like various interesting properties. So if you suddenly lose power, you know, and you do half write into a file, this half write kind of either happens fully or never happens at all. So this atomicity is there. We'll talk about file systems as well. So file system is part, and this is kind of it. So essentially, if you draw a diagram of a typical Linux, Windows, or a Mac OS kernel, you will have this application itself, which will have this main function, right? And we'll have a library, which will typically is called the libc on Linux, right? Which provides the interface to access the system calls. there will be this boundary which isolates, so application cannot write memory of a kernel, right? This is not allowed. The only thing you can do is you can invoke a system call through a protected entry mechanism, kind of like a TSA screening at the airport. You will get screened on the entry saying, okay, you bring in something illegal or dangerous, no, then you can get in. And inside you will have those layers, so kind of like a file system, ext3, which sits on top of a block device, which really a device driver, which writes into those magical memory location to, instead of like printing a letter H on the screen, it will initiate some transaction with the disk device, and the disk device will go ahead and read some data and will put it back into this memory, right? You will have a stack of network protocols like sockets, TCP, IP. I'm sure some of you are in the networking class. There will be low-level Ethernet device driver. Again, same idea, low-level interface to the device. Remember, I said that the operating system hides the complexity of the hardware. There will be a component which manages physical memory. Remember page tables, I just mentioned them. And each process will have its own page table. And there will be a scheduler which will be deciding which application runs next, right? So this is essentially a high-level diagram of a typical kernel. And this is our goal for this semester, to essentially understand how this yellow part is built, something what is called the kernel, and how kernel launches applications and runs them in memory, right? Any questions? Okay, good. And as a kind of a fun activity, I wanted to show you something. So one way, and again, that's kind of, remember I said this MIT class on which would base our class was designed to learn by building, right? So the idea is that similar how you learn a language, you start by doing hello world on the screen, right? And the idea is that the best way to learn is to build something and make sure that, you know, if you build, you understand how it works. The question is like, how hard it is, you think, is to build a piece of software which will boot on a real hardware and will print hello world on the screen. So the goal is to essentially do that. So this is the link to the Git repo. Let me just show how it looks. Where is it? Here. Hey. No, this is wrong. So if I clone this repo, I did it a couple of years ago. Essentially, what I will be using, I will be just using just one single file, this boot.sm. If we go inside, you will see that it's a very, very simple thing. So I don't know how much assembly you know, but this is says, okay, there is a start label, and it's an entry point into this program. And what it does this move instruction. And so move instruction moves a value, this 0248 in hex, which represents capital H, into a memory location at 8000, right? And then I say now it's E, and this is the numbers. There was again an agreement between the hardware manufacturers and the software. They created a table which says, okay, this number, I think the total number was, I forgot, I would say 256, but now I think it's more. So this table is called ASCII. Don't ask me what it stands for, but essentially these numbers represent letters. So the hardware manufacturer, which builds a VGA graphical card, will say, okay, I will render it into shape of letter E and we'll put it on the screen, right? And so hello world, just like that, right? So, and here I halting the CPU saying, don't do anything after that. So I have a little bit of tooling here, which is done with this make file. Our probably first homework will be to learn a little bit about make files to just understand. But what it does is roughly saying, I'm building the kernel target here in line 11. How do I do that? I take assembly object files in a linker script, and I will invoke this linker command. Linker script allows me to like do a little bit of magic, but essentially, since my assembly files, this one is just the single, all the SM files which have the SM extension, and I have only one, boot.sm, right, which we've seen. And there will be a little bit of, again, magic if I say make make clean. So delete everything I do make. This is the exactly commands which my machine executed. So it converted boot asm into an object file, because asm is a human readable assembly, which I typed, and the object file is actual machine instructions. So this assembler actually compiles from this human readable into machine instruction. And then I have to create a special header which lets the bootloader know that what I'm compiling is really an operating system kernel. There's also a protocol agreement of how things should be laid out in memory to make it run. And this linker essentially says, okay, take this boot.o and a multi-boot header.o and compile them into the kernel.bin file. That's my actual operating system kernel, which consists of like this 10 instructions which print hello world. And the linker script essentially tells me, remember, I told you that there will be some magical locations and stuff like that. So I play this game a little bit here, right? So anyway, so there is this, if you look at the README here, it tells you what exactly you have to do to make it compile. What do I have to do? Actually, let's switch here as well. So says make QEMU. No, we don't want QEMU. We want to, it can run in an emulator, but really want to run it in real physical hardware. So let's see if what do I have here? Did I get it? Oh, build. So this is my kernel, right? And what I will be using, I will take this USB stick, which is, I will use it to make sure that I can boot from this USB stick. So I'm plugging it into my machine. You have to be a little bit careful. So I don't remember, like each machine will have a slightly different mapping of those devices, right? So, and so what I do here is I try to figure out what device did I get here? And it says, okay, it says nothing, don't do anything, but what happened is that I actually got this SDC device. It's right here in my def SDC, right? And so I have this instruction saying I will copy this. What I build, actually, I build since my bootloader wants to understand a specific file system, which is this ISO file system, which what used to be used on this optical drives. You can choose, make a different choice, but this was one of the easiest one. So I will just copy this hello.iso onto my USB device, but you have to be careful with substituting this line, this command with the actual value of your USB drive, and don't overwrite your root disk. So let's quickly do this. So we do, what did I say? I say SDC. Like this, right? Just to check that we are on track, we can do fdisk, like maybe sudo fdisk -l, just to check quickly that we are writing into actual SD. Why? That's scary. Can I type my password? Yeah. So it says 3.8 gigabytes. So that's my USB stick. So I'm safe doing it. Just otherwise, you know, I can overwrite my root disk. So okay, let's do this. Where is it? Where's my build? I forgot to probably build this ISO. I was saying, let's say how, let's say how I can build this ISO, make ISO probably. Forgot to build this CD drive file system. So now I'm good. This is blinking actually here. I'll do a sync command just to make sure that everything gets written and I can actually unplug this thing. And then I will be using this wonderful machine, which is a prehistoric Lenovo laptop, but it still boots. So the reason I'm using this one, because first if I reboot, obviously you will lose the recording, but the other thing is that I'm not sure that I can actually, that this escape format works well on this, the first machine. So let's make sure we can actually, let me stop sharing my screen because nothing really is happening there, but instead like use this camera, kind of maybe position it on this screen. I don't know. No, not very usable this way. Oh, nice. We just have to pray a little bit. Will take us just a couple of seconds. So, yeah, it says it will predictably say fan error, but we can overcome it slightly by saying escape. Here it's a grab bootloader, so I cheated. I didn't really use just my kernel to boot. I need a bootloader. Bootloader is a piece of software. Can you see anything? Probably nothing, right? But we will have to play a trick. So I have to input a couple of commands here to make sure that the commands. Oh, I'm still sharing my screen. Oh no, here, not sharing for Zoom, but what I need to do, I have to type something like this: set root to be HD1, and then maybe do something like set kernel to be, and there are ways to make it faster. Boot, we're almost there. Kernel bin, then do this multi-boot specification number 2. Kernel, another one. Why? And if I say boot now, so this is a magic of truth, a moment of truth. Let me see if it will actually boot here. So pressing boot. Yes, no? B is not a command. Oh, hello world. Yeah, success, right? So at least everyone is awake. Just to keep it a little bit more exciting, this will be a homework number, maybe 2 or 3. So I mean, it's not as hard. Besides that, I will ask you to boot a little bit more functionality, but you will get to main essentially, not just some assembly commands, but you will get to main. And you will get extra credit for booting on real hardware. You will have to provide me a video. Be careful with real machines, though. But if you have something, we'll do that. Okay, thank you. So we'll stop here. We'll start on OS interfaces next time.